Score syllabus, guys.
We went over this the first day of class. I know that was a couple of weeks ago. But I'm having problems with this section right here that talks about topic quiz homework.
The online topic quizzes must be completed within 7 days of completion of the lecture on that topic. After 7 days, the online quizzes will no longer be available. Links to the online quizzes are provided through Blackboard in the chapter section of content.
How many people have been doing the topic quizzes? Huh? Nobody.
I knew that was.
Nobody. Nobody in the class has done any of the topic quizzes. And they're not very long. They're maybe 20 questions inside that chapter, which will help you greatly on the test, because the tests are multiple choice, and where do most of the questions come from? From the topic, from the chapter quizzes. So inside the, let me see, Blackboard. So when we go into course content, these are the things that we're studying. So here's logic functions. When you go inside logic functions, just like it says, we have a topic quiz, and here's a topic quiz. And there's going to be logic. So the gates, functions, exclusive or, exclusive nor. And so there's 70 questions here that would be inside there. So what I'm going to do, and unfortunately, and I'll put this one, I'll actually post this since we're having problems, is I'll give y'all for Friday, midnight Friday, to finish all these. Yeah, well, the comparator is on the test, but the topic quiz won't be due until next Tuesday. So the topic quiz on what we're going over today won't be due until next Tuesday. But if you want to go ahead and do that, then that'll be questions off that's going to be on the test too. So here's a review for the actual review for the test. Of course, you got to see what's on there.
Hopefully y'all do okay. So all the logic functions are going to be on there, all your timer. What's important in PLCs is a lot of people forget that this is electrical controls. And we've got two contact symbols in PLCs. We have a normally open and we have a normally closed, and that's it. But when you get to the wiring diagram on how you wire up the PLC, they use the electrical symbol for these devices. You'll understand that. And they do this in your book quite often. So if you don't understand the electrical symbol for the devices, then you wouldn't be able to look at the input, the actual input wiring, and tell what's actually hooked up there. So of course, some of the important ones, of course, it's timers, flow switches, and there's a real good chapter. But I'm looking on page 183 in the textbook. Y'all need to know those symbols, which is the symbols on the 4 different types of timer contacts that we could possibly have.
So 183.
Yeah, 183 in my book. I think everybody's still got the same book that I've got. Now, the nomenclature that they use in the textbook is not actually the nomenclature or the way we do these in the actual slides. I mean, on motor controls. So if it points toward the switch, it's an on delay timer. If it points away from the switch, it's an off delay timer.
So these two are on, so if the arrow points toward the switch, it's on delay. If it points away from the switch, it's off delay.
And in the trade, we call this a, anybody remember that had motor control? We call this a normally open, closed. And this is a normally closed timed open. And then this right here would be a normally open timed open. And this right here would be a normally closed timed close. So what you gotta do is picture, this is an on delay timer, right? You understand? So it's normally open. We put power on the timer. What's it gonna do? After a time. Yeah. So normally open time, closed. So notice on your on delay timers, it's backwards. Normally open time, closed, right? Normally closed what? Time's open. On your off delay, they're the same. So when I energize an off delay timer, this contact closes instantly. Oh, I'm saying, when we take power off the coil, it's timed what? Open. And this is a normally closed time close. So they don't actually tell you when the timing occurs inside our textbook. They say normally closed off delay timer contact. But the way we nomenclature it in electrical, they tell you when the timing occurs, right? You understand? So normally open, timed open, normally closed, timed open, normally closed, normally open, timed closed, normally closed, timed open, normally open, timed open, normally closed, timed closed. So long delay timers, they're what? They're opposite. Off delay timers, they're what? The same. You'll probably need to make a little note in your textbook on that. If you keep this textbook, this is a pretty good textbook for Allen Bradley. But it wouldn't be too hot. Even though when we were at that thing in Tennessee, there was a guy that says they teach the Siemens PLC, but they use this book, which is pretty good because that way you see how two PLCs actually do the different things. But to me, it would. So the and, or, nans, nors, nots, are y'all okay on wiring contacts and their logic? Everybody okay on those? And, ors, nans, nots, exclusive ors, exclusive nors.
We like good on this. And out this slope.
Oh, we're not going to do any reduction in this class. So, so we're not going to do any Boolean algebra. We're not going to do any Karloff maps. This guy's going to come in with the background. So one normally closed contact by itself is what type of logic? And then the two normally open, or multiple normally opens in series. These are what? Now this is and. Multiple normally opens in parallel. This is a what? No. No. This is the or. If any one of those.
You're open, I didn't see that. Okay.
Take your glasses off and clean them real good, see. Normally closed in the series. Now this is a NOR. Normally open, normally closed in parallel. There's a NAND.
So the middle one is an and?
Yeah, this is an and. Now remember, nans and nors are what's required to make the output false. Y'all understand that? Ands and ors are what's required to make the output true. So here it says all these have to be all, and if I use the term all, that means it's an and. So up here it says all these have to be closed to make the output true. Down here, if I use the term any, that's an or. Y'all understand that? So any input will cause the output to be true. When I get over here, we're trying to figure out what's required to make it false, too. So any of those, if any of those open, the output's false. So let's ignore. All these have to be open for the output to be false, right? You understand that? On this one, what's this one? So this guy right here, we got two exclusive symbols. By the way, how many inputs can a AND gate, AND function have? How many contacts can I put in series? How many contacts can I put in parallel? Huh? How many contacts can I put in parallel? No, tons. Put them in parallel. One per line. We can have many per rung, but one, right? Okay. How many contacts can I do for an exclusive or an exclusive NOR? Two. You see? Because what we do, these guys, these are comparators. So we can tell what's going on. Now the output of the symbol, if it's got a bubble on it, that means it's low active. It's true when it's low. If it don't have a bubble, it's what? False. What these guys do is tell you what goes on if the two inputs are not equal. So if I call this A and I call this B, if the inputs are not equal, the output will be high. Right, you understand? If the inputs, if they are equal, I'm sorry, what I say? If the inputs are not equal, the output will be high. If the inputs are equal, the output will be low. That's the OR. The NOR says if the inputs are not equal, the output will be low. If the inputs are not equal, the output will be low. If the inputs are equal, the output will be high. So that little guy right here is telling you what you get if the inputs are not equal. So what do we get out of this?
If the inputs are equal, the output is.
Depends on which one you're looking at. So on these symbols, what the active state of the output shows you is what you get when they are not equal. So on this one right here, if the inputs are not equal, I get a 1. If the inputs are equal, I get a 0. On this one, if the inputs are not equal, I get a 0. If the inputs are equal, I get a 1. And this is what gets people confused, this little bubble they put on the input, because they're thinking true and false and that kind of stuff, right? So right here, if I close A, then this is going to, if A is energized and B is not energized, this right here will close. This right here would open. So I would have a path through here. All right, you understand? Right, you understand what I'm saying? Yes, sir. So what would happen in so if A is true, then this will open, this will close, and the output would be true, right? Okay. If B is true and A is false, then this guy here would close, this guy here would open, right? And I got this path right over here. right? You understand? I erased too much of this. If A and B are equal, if A and B are equal, right? Oh, I messed up. Dang it. Still messed up. And what you do is you just swap them over. So up here we use a what? Normally open. Down here we use normally closed. So if A and B are equal, that means this right here would open, this would close, this right here would open, this would close. So we get a false. So we get a true if they're not equal. So that's not true. We get a high, we'd say true, we'll call this a high. We get a high if they're not equal. And we get a low if they are equal. That would be an expensive one. Well, how would we do the other one? Anybody seen that? So this would be a lot. Yeah, so if you get 2 zeros, this is true. Right. So here, yeah, so this would be, and that's the way we wire it. We get logic out. Now, the exclusive OR and exclusive NOR can only have 2, how many contacts? Well, 4 contacts, but they're controlled by the same output. Of course, back in the intro to PLCs, this is where you learn the Boolean algebra. So if you can mathematically express a circuit and either do it in a Karnaugh map. The problem with Karnaugh maps, and I hate them things with passion, is that if you get over 4 inputs, you're going to have 16 entries in your table. If you go to 5 inputs or 5 control devices, you end up with 32. You go one more, you end up with 64. And so you get a table that's so dang big, it's hard to figure out what goes with what, all the rooms and the corners and sides and stuff like that. Now, anything below 4 inputs, so they don't reckon that, they don't suggest you use Karnaugh maps on anything below 4 inputs. Boolean algebra, that's mine. So Nancy likes Karnaugh maps, I like Boolean algebra. So if you can mathematically represent this and you know Boolean algebra, what can you do? The equation can reduce. And this is what really, really got me into algebra, is actually seeing Boolean algebra. And it helped me in algebra too. Is realizing when you reduce an equation, you're actually reducing a circle. You don't understand that? So if you can mathematically represent a circuit, and then you're able to reduce the math equation, then you're literally what? Making a smaller circle.
That's an exclusive.
Yeah, because if the inputs are equal, so if the inputs are equal, we get a true. No, this is not an OR, this is a NOR. If the
That one right there.
yeah, this is X, we call this X NOR. This is called X.
And that's all.
Yeah. That could be the symbol up here.
So today we're gonna look at compares, jump, and master control resets. Now this is where we really jump from motor control. So what we've been doing right now up until this time is everything you've done, you can do with relay. Logic has been around long before we had logic gates, which is what we deal with in digital. Ands, ors, nots, and nors was originally done with this. We had some stuff out of US Steel that was language, they call them NOR packs. And these were actually just packs that had these little relays in them where we could do NOR, NANds, and NOTs. Well, NORs and NANds, by the way, are what we call universal gates. Universal gates means you can get all the 5 basic logic functions out of NANds and NORs. You can wire NANds and NORs together. So those are real popular. We used to teach them here, but that's all the tricks I've ever seen in old. But what we get in PLCs is we get a computer. And what we can do with PLCs that we can't do with relays is we can't do what? Compare. And we can't jump. And of course we can do a master control reset. We could have a master control relay, which is basically the same thing as a master control reset. If y'all remember that. So what I'm going to show y'all is I did the lab that y'all were supposed to do. Some of y'all didn't do right, but I'll let y'all get by with it. So let's look at the lab and see that we're working on, which is lab 3 if you hadn't turned it back in. But and what's the requirements for the lab? You have to have a master start stop. Some of y'all tried to, and I'll let y'all by with it, is you actually use your first contacts as your master, and that's not the way it's supposed to work. We're supposed to have another master start stop. They call it a master switch. And then the master switch is supposed to enable everything else, right? Some of y'all use the master switch as your first mode. So this is the way we do a master switch right here. Well, anytime they say a master switch, we're going to use a master stop station. It's also called a 3-wire control, also called a memory circuit, and also called a cylinder. So that means nothing happens until I do what? And then we start it with a push button that they call on. They call it green. This is not fun. No, this is the one that's in this is Logic Pro. I mean, this is RS Logic. By the way, we're calling RS Logic. The name of the application is actually RS Logic 500, right? Which has nothing to do with the 500 PLC. It's just like, it's a program, it's an application program. That's all it is. It just happens to have the same number as some of the PLCs that we use. And they're not actually 500 PLC. They're 5, we got 5/04. So actually we call them 504, but they're actually Series 5 version 4. It's just like Siemens calls their Step 7, that's their application. Has nothing to do with programming a Series 7 PLC, right? So this is the 500 series of this application. This is for the one, let me bring up the other one. This is in Logic Pro, because I couldn't find my switches. So what's supposed to happen here, we're supposed to have a master start stop, or a master, we call it master start stop. The book says a master switch, which we should do this. And what we're supposed to do, I'm going to stop it. You know, what's supposed to work? So we're supposed to enable the thing with a master switch. And then we have another push button we call PDG, I think it's supposed to be. Yeah, green push button. And unfortunately, we can't change the push button colors. And then instantly, a green light's supposed to come on and the motor's supposed to run. And after so many seconds, the next 2 lights are supposed to come on. This light's supposed to blink 3 times. And after that finishes, that's what 6 seconds after it finishes. That was what was interesting, is trying to wake that thing. Using a single timer, trying to use a single timer interested in what we do. Now, I'm using one timer to time this whole thing. One timer. And this right here is 5 runs code to do this. And notice what I'm doing. I'm using compare instruction. Okay. By the way, we need to understand what we mean by inputs and what we mean by outputs. Y'all know y'all's timers are what type of instruction? They're output instructions. Right? You understand? Contacts are inputs. Compares are they're over there. Compares are input instructions. They're on the left-hand side. So your timers, your move instructions, your math instructions, those are all output instructions. Math instructions are output instructions. So output instructions go where? Yeah. Now Logic Pro will let you get by with a lot of stuff. You can put math instructions anywhere, but that's not true, right? Because it's output. So if I just stuck a math instruction in here anywhere, then I'll get into a lot of problems with RS Logic.
So, not being redundant, TEQs are compared.
Well, that's what we're fixing. These are compare instructions. And we're fixing to get into those. Yeah, the trick was to make that thing pause. So I'm using one timer, but the problem is trying to get it to pause after that bell rang 3 times. Using one timer. So what I used was what type of timer? Retentive timer. So that means I could pause it. If I disable the regular timer, it would reset instantly. But a retentive timer, y'all can watch it run. So I have to start the whole thing. I have to reset it, right? Start it and do this. But you can watch this timer pause like this. So it waits for the bell to ring 3 times. If that was the regular timer, if I tried to pause it, it would do what? It would reset. So that was one situation where we used a retentive timer instead of a regular. So what's the difference between a retentive timer and a regular timer? Yeah, if you don't enable, so when the enable for Allen Bradley, this is not only start timing, it's also enable. So this one contact serves 2 functions for the Allen Bradley. You can see some of the timers, like on the Siemens, it's got an enable input. So not only do you tell it to enable it, you have to enable it and do what? And also tell it to start timing. Of course, you can connect the inputs together. A retentive timer, when we disable it, it does what? It maintains its count. But how do we get rid of that? Well, so retentive timers, you have to reset it. So making it pause was interesting. And I realized that when I moved from my,
I was trying to see where did you get that bit that you made pause?
We'll come back and look at this after we get over these. So compare instructions. This is what we can do with a computer that we can't do with jump instructions. This is what we can do with a computer that we can't do with a relay logic. Okay. This is what really gets us into some high power stuff once we add the computer capabilities. Use a compare instruction to energize a coil. We can use a compare instruction to energize a move instruction. We can use a compare instruction to energize any output instruction, right? Y'all understand that? Any output instruction. Cascade compare instructions to set upper and lower limits on a control system. Use jump instructions to do what?
Skip around.
Skip around in our program. Use multiple jump instructions with multiple label instructions in a PLC ladder logic diagram. So we'll look at this in a minute. Jump instructions is what we call an instruction pair. So what does that mean? You can't use one without the other. So jump label is a pair. So there's several of them. We have instruction pairs.
So you can use jump by itself.
You're gonna, Allen Bradley will probably come up and give you an error. I don't know what Logic Pro will do. but Alan Bradley will probably come up and give you an error and a run. Because you cannot have a jump without a lock. Like, that would be like people telling you to go and not telling you where. Right? That makes sense? That's like me saying, okay guys, I'll meet y'all there. Let's go. What good does that do, right? Yeah, don't have, yeah, so labels, jumping labels are a register pair.
The labels are
Where we go to,
registered
no, it's an instruction.
or instruction.
But it's got to use use compare instructions to energize jump instructions. We call these conditional jumps. So this is where you really get into power, where your program can actually make a decision. So you might want to loop through runs while you're loading up boxes, right? You understand? You want to load up 12 items. So you would loop until it did what? 12, and then you might drop down and start the whole series over for the next request. So these conditional conditional jump instructions is where you get power. Use a master control reset instruction to halt the operation of a section of a PLC ladder diagram. Are we okay? So these are the compare instructions that we have available to us. Is we have, Alan Bradley calls it EQU, which stands for what? Equal to. NEQ is, okay, LES,
That's the answer.
yeah, GRT,
Greater than.
okay, LEQ,
That's the or equal to.
GEQ.
Greater than or equal.
And then also they give you the little mathematical symbols. So remember on these, the big one is pointing forward and the small one, right? Understand that.
A is greater than B.
Yep. And then we can combine these to actually set up a range, which is really, really neat. When the PLC is scanned in a ladder logic diagram, sometimes where I'm marked, it should be scanned. When a rung is not scanned, state of the instruction on the rung remains the same. Conditions for skipping over rungs can be generated either by the state of an input contact as well as the result of a compare. So this is an example of a equal range. So here we're looking at a register, again, N7. What's our N7 data register? Now these are integers. So what we have on these is we have two things. We have a source A must be a register. Source B can be a register. It could be accessed from a register. Remember, we have three what we refer to as addresses. What are our three addresses? Immediate, direct, and indirect. I know they call it indirect. I'm trying to get my microphone. So this would be register address. Immediate, we would actually have the number. So source A has to be a register. So we got N7 registers, we got bit registers, so the B3 and the B10 registers are bit registers. We have R registers, which are control registers. We have F8s, which are what for microprocessor. Logic. R is logic. What's F8? What's F8? The F8 data registers. Those are our floating points. Y'all understand the difference between integers and floating points? Integers are whole numbers, right? You know, they use signed whole numbers. And then 116-bit register for these, which means, and it's signed, so that's why we get the 32,768 negative, right, and 32,767 positive. Floating points are two 32-bit registers, two 16-bit registers, so that's 32 bits, which is huge numbers. And then, the F8 registers, you can also use scientific notation. So they get us way up in the billions, right? Should be any number we possibly do. But floating point means these are numbers with fractions. They can have fractions. They don't have to have fractions. And then integers are no fractions, but they still are signed numbers. So here we're bringing the info, source A is the what? Has to be a register. Contents for a register. So this is what we call register or direct addressing, right? This can either be a what? Can be
Register
a immediate addressing or a number or access to a register. Who or by register.
So source A is direct.
Yeah, this is direct. So we can use direct or we can use indirect. If you see the hashtag, which we call that, which is that means it's using indirect addressing. Which later on, we'll get in more detail in indirect addressing when we get into sequencers.
You said a number is
Immediate. So if it's actually got the number, we call, Algebra refers to that as immediate address. If it's got a register that contains the number, then we call that direct address. If it has a register that points to a register that has the address, then that's going to be indirect address. So the only one we're concerned with right now is immediate and direct, and we'll get into indirect addressing later. But immediate means immediate we have constants, right? You understand that? Direct, this register contains the operand. On indirect, this register would contain an address that points to the operand.
It all be indirect.
That's indirect. So we get the address indirectly for a register. We have an index. We actually have 4 addresses in those. So indirect. So I told y'all wrong. So immediate, then we would specify the what? The number. Direct, we specify a what? That contains the number. Indirect, yeah, we specify a register that has the address. I'm running out of room. So what we would do to specify this, if this was inside brackets, that would mean that's indirect addressing. And then the last one that they talked about is index, and this is the one that's a little harder to understand. Ron, look that up.
Indirect specifies the register that contains the address.
Yeah, what contains the address of the register that contains. Okay. We had brackets around it. That means N7 doesn't have the operand. N70 doesn't have the operand. N70 has the address
of where they might have that. This is directly. So to get it, to specify, indirect address and the registered address to be in one.
So you're gonna,
Yeah, it'd be in bracket. And then if it's indexed, it's gonna have the hashtag.
so the index is a note, is another one, right?
Yeah.
Index, uses something called a stack. Index is, when we have to go through tables or arrays, normally we use index addressing. Because, index addressing is kind of like when you walk into these, food bars or these cafeterias, where you have all the plates stacked up there. And the only one you can get to is the one on the wall, on the top. And then they all, LIFOs, last in, first out, first in, last out. So we use index addressing to go through arrays or tables. And that would be a group of operands that I put in multiple storage locations. And instead of me specifying an address, we can use a register we call an index register that will automatically go through those arrays. All I have to do is specify the top of the plate. And it does what? It'll automatically pull those things out of that array and put them in there for you. But we won't get into this until we get into sequencers. Sequencers is when we have a group of data that we try to go through that makes an operation operate in a very complex sequence. Used to, we had sequencers were kind of like drum switches. Let's see if it's open. What we would do is we would put tabs in the thing. I don't see it. We do. We got a sequence up here that's really good. But it was motor driven. You had tabs. You had metal tabs on it. And every time you rotated, it would bring in a sequence of relay. And all you'd have to do is just what? Change the tabs. You can change the sequence. So we'll use a sequencer. We'll program. It might be back on the table. I'll see if I can find it. Supposed to be in this lab for showing. But how we get to it? So immediate means this would actually be the what? This would be the number I'm going to compare it to. If I'm not going to compare it to that number, it's going to be somewhere, then we're going to specify another way, either directly or indirectly or indirectly. So this PLC and understanding the addressing modes of a PLC is very, very important because this is how you address those operators.
So the brackets will only be used in indirect address?
Yep. So brackets for indirect, and I'll go back and double check that. I'm pretty sure I got some things. I'm almost sure it's brackets. Well, let's look up addressing modes real quick. So
Before I go too far down this path. Of course, we could probably look it up in the they don't talk about addressing modes. I know it's in here. I just don't know where to. No, address decoder is something that deals with microprocessors. Oops, wrong. So all these manuals are up there actually for you. And of course, and so if you really wanted to get into more details, the time it takes for these different instructions, and yeah, I don't see it. I don't see it. I'll find that, and I know it's in the textbook somewhere for those, the address and those.
And the motor.
Huh?
You saying the motor? Is it on 132?
No, it's not motors. It talks about how we can address the operands. This book right here, no, I don't even see it. No, I'll find it later. I'm pretty sure it's right, but like I said, I'll find it where we can. I'm almost sure of the brackets. The only one I'm concerned with is how to specify it in Greek. Well, index address and we'll use what we have affectionately known as the hashtag now, right?
Must it be in front of the register?
So if we came over here and did this and put it right in front of the register name, that's going to use index address. And sequencer instruction that we'll get to later on uses the index address, and so we'll get into it in more detail then. So this is NEQ. So everybody okay on equal? Isn't that the first one they got? Any questions on that?
So N7 is equal to N1, if the contents of register 70 and N71. Now this is specifying, if we don't specify slash, what are they talking about?
So normally this whole time we come up here and I'll say output, and then I'll say colon, and I'll say 1, and then I'll say a slash 0. If we put a slash, what are we addressing? Yeah, so this is the word, and if I put a slash, we're specifying the bit within a word. Okay, you understand? If I come over here and say this, then what am I specifying? I'm specifying a word, right? You understand that? So I'd be working with 16 output ports at the same time. Now sometimes we have to address a word. So if I've got counter 5, this specifies which counter, right? You understand? And then I can come over and put a slash, that would be a bit. But
I have to actually specify a 16-bit register within the counter. Y'all understand that? Okay, so this is a counter number. Every counter, by the way, takes, I think, 3 bytes of memory.
It's on 296.
Yeah. So the dot was, so I could come over here and I could say dot 0, right? You understand, but that would be a waste of time because this is the whole word. But when we get inside a counter or a timer, we have several 16-bit registers in there, so we have to specify which register we're actually going to, right? Everybody understand?
It's on 296.
So when I say N7 colon 0, we're specifying a 16-bit word, right? You understand? Here, this is specifying a 16-bit. If I want to specify a bit within that register, then we use the slash.
Okay, with the counter right there. C5, colon, 1, that dot is supposed to be slash.
No, it's supposed to be a dot. The dot means 16 bits. The accumulator is a 16-bit register,
Well, that applies to counters.
counters and timers.
Okay, but when we're doing outputs and inputs, well, just outputs, that's what we're writing.
Yeah, because we don't have to specify which 16-bit register, because this is the address of the 16-bit register. But when I get into a counter, how many 16-bit registers does the counter have? At least it's got to have an accumulator register, right? You understand that? Now the done is a bit within a 16-bit register, right? You understand? Counter done, count up, those are bits. So how do you specify the bits? So if I wanted to get to the done bit, if I wanted to get to the done bit inside counter 5, I would put what?
C5, colon,
Slash.
Now here I want to access the entire accumulator.
No slash, just dot.
Dot. Got to put a dot. But I don't do this right here because an output address is a 16-bit register. A counter has multiple 16-bit registers. So when I say counter 1, I have to specify which 16-bit register I'm interested in, right? You understand? So we have to put the dot. Got the preset register is a 16-bit register.
One is for that.
We have the accumulator, right?
Yes.
Preset. We can look it up, but there's actually more than one. Preset, accumulator, they do call it accumulator. And then we have the status register. The status register is a single bit. So when you put the slash D done, you're accessing a bit within the status register. So every counter has 3. Timers might have 1 because timers we have that time base too, right? So this could be, my source could be the accumulator register in my account. So how would I put that? I would put like C5, right? Colon 1 dot ACC. So we're talking about this right here. This could be the register in a timer. It could be the register in a counter. It could be the register. It could be a floating point register. It could be a control register. It could be a integer register. It could be status registers. Anything that's addressed. Could be a bit register, right? You understand that a big 3 register? One of the big 3 registers. Big 3 or big 10.
or it could be a number.
Could be a number. This has got to be one of those things, right? You understand? This could be either what? A constant or a number. I mean, a constant or a address. That's all I'm gonna say. And that's the thing too. So this is saying if the contents of source A, no matter where they come from, is equal to the contents of source B, then this guy here would be true. And right now that's going to energize output 0 colon 0. Very simple. Then we got this guy right here. What does this say? So this means that the constant, however we get source A's gotta be somewhere else, right? You understand that? Gotta come from a register somewhere. Source B can be a what? Number or register. But this says, okay, if these two things are not equal, the output needs to be true. So before that was true, when that one was true, this one here would be false. So we wouldn't combine these two on a single run. Because if we combined them on a single run, it would never be true. Okay, what does this say?
Less than.
So if
Is less than
Yeah.
source B.
if source A is less than source B, now notice they actually put this, remember the arrow points towards the smaller, right? Are you okay there?
Yeah.
Any questions? Greater than,
Source A.
so we could combine a less than with a greater than. Right, you understand? So we can say if it's greater than 5, but less than 10. And then it would be true between what? 5 and 10. Between, not,
So 6, 7, 8, 9.
right. We can include it, we'll put, we use greater than or equal to.
But why were you saying put them on 2 lines? Yeah, well,
No, on the same line.
on the, you were saying that,
I said we would never come up here and do this. I'd never come over here and put a box right there and use a less than right here. No,
would never reach, it
never be true.
would be under the next one.
Well, it would be on another run, or we could,
Line.
if we put them in parallel, if we put them in order, it would always be true.
If we put them in, right, you understand? So I wouldn't use these two together, either in a different line, not in a different run, in a different line. So we'll see later on, we can actually put them in parallel with each other, right, you understand? Or we can put them in series. Normally we put them in series.
Not using the same source, but if you were using a different source, could you do it?
yeah, but so you could say, that's a good point. So if we, over here, we was using N7 and N0 and N1, over here we was using what? Yeah, N5, and, N7, 2. Can't use N5. And over here we was using 53. Yeah. I do that all the time, basically. So yeah, we could use them if we're comparing two different operands. LEQ,
Less than or equal to B.
Less than or equal to. So if source A and source B are equal, it would be true. Or if it's less than, it would be what? True. Okay, let's take a breath.
or greater than, equal to. Any questions here? Greater than, what's this? Everybody understand that? Are you okay? Questions? Comments? Everybody okay? Greater than or equal to?
So if source A is greater than or equal to source B, then this line would be true. Any questions on this one? Combine and compare instructions. So here we're setting a range, right? So the first one says if
Source
A is greater than B, B is 100,
source A is coming from, the A is gone, by the way, in this example. Y'all notice that?
Yeah.
But it's supposed to- Source A, this is probably a Logic Pro instruction. Sometimes Logic Pro is not perfect on what they do. But if source A, which is coming from direct addressing, it would be N7, word 0, is greater than 100, then this would be true. This says if it's N7, word 0 is greater than 150, this would be true. I'm sorry, less than. So what would this would be true between a range of what? 101
to 149.
Now 149. And then it would count up, right? Do I understand that? Yes or no?
Yeah.
Well, okay, right, it's gonna be,
Count up. So every time this was true, we would count.
So when they're in series, both of them have to be true.
Right. Get through. That's exactly right.
I thought
If they were,
I thought just said we couldn't use the same source in that.
no, a while ago, if we said less than and greater than, and use the same source. So we were talking about something else, Kathy. So I couldn't come over here and say, greater than, and then put that into a less than and equal, right? Understand? Because let's say we say greater than 3 and less than 4. The same source. This would be set greater than 3 and less than 3. Right. So when this was true, this right here would be false, and when this was false, this one right here would be true. So this is what we're talking about here. Here we're using greater than and less than, but both these numbers are what? Yeah, they're not the same.
So is it not a function that you can do the range in itself? You have to use two different ones.
For this PLC. I'm not sure about the Siemens PLC if they've got one that combines it. But this makes sense because the more instructions they make available, the more you have to learn, right? So we have how many? We have very few instructions, compare instructions, but we combine them, either put them in series or put them in parallel. So if we put them in parallel, it would be if this or this is true, right? You understand? If we put them in series, it's going to be what? If this and this. So using our ands and ors, we could set up a mass section of compare instructions that we could get the output from whatever we wanted. I can't think of anything.
So it could be a number. That number relating to anything like negative minutes or just a
No, it's just a number. Yeah, it don't have any units. Where it comes from is up to you. But a number is just a number. It's not milliseconds. It's not seconds. It's just a number that we're comparing. We're comparing two numbers.
Using the N7 registry, it's going to be a whole.
Got to be a whole number, not a fraction. And we run into that a lot, where the math gives us a fraction, but we don't need the fraction, right? Does that make sense? I've got one I'm working on, RPMs. I'm trying to come in with an encoder and get RPM set up. I'll show it to you. So it actually displays. Well, see, you're going to use integer. Normally we don't display fractional RPMs on the display.
See, it can come from anywhere because if you're using a pressure switch, you got pressure gauge.
Now this pressure, that pressure, but it's not PSI. It's just the numbers
That's the number that you use.
that you're getting.
You're getting it to the system to convert it to what you want to use.
So the number could be anything. It could be seconds, but it's not considered seconds. It's just considered to be a number. That makes sense? So I'm comparing this timer to that timer. Well, I'm not comparing it to seconds. I'm not comparing it to minutes.
I'm just comparing it to the numbers that's coming from those timers. Now, the timer might be in minutes and it might be in seconds. Does that make sense?
These units don't matter, just
Just the number. These guys don't care where the number came from. It's just comparing one number to be greater than or equal to or less than or equal to. Where those numbers come from, they can come from an input poll. You know, they could come from not from a, they could come from a counter. They could come from a timer. Or they could come from a register, the result of a math operator. Right? Or they could come from anywhere. But this guy here don't care what they are. All it's doing is comparing to them. So what does N7 contain?
Yeah.
But what could be in there?
Anything.
It could be, it's a whole number, but it could be a time, it could be a count, it could be, right? This could be, we could bring this directly from a calendar, we could bring it from a timer. So all it's doing is comparing these numbers. All we know is they're in registers, so we know these guys can't have one.
Say again?
Seven registers.
They can't be equal. The numbers can't be.
They can't be practiced like that.
Oh.
Well, they could be the same. I mean, what if I had, huh? It's gonna be between this range. But I could have, you know, this could be, these numbers are gonna be different.
That's what I meant. That's what What we're doing is want to make it go true, right?
Yes. And we can combine them, we can combine, if we put them in series, they're considered to be ands, right? If we put them in parallel, they're considered to be ors. So we could say if it's greater than 100 or less than 50, 150, you know, that would still be, but if I was looking for that situation there, I would put them in what? I would put them in or, which would be what? Parallel.
So, and nor is that gonna be your pretty much exclusive function.
No, these are not exclusive functions. They're exclusive.
How would you get and nor?
You wouldn't use them on compare instructions. You would have to, you would have to go through, contacts or something. So, ands and ors are basically, compare instructions. We're trying to see if something is true or not true. Are we okay? But I guess if you thought about it, you could probably implement an exclusive or, exclusive ors for these guys. Without using contacts. I think I did a little Logic Pro program. Hopefully I uploaded it. I think I did it at home. Says it's already running. And I opened up the Step 7 software today. Oh, there it is right there.
No, this is not the one I wanted to show y'all. Dang it. This is it, I guess. Doubt I didn't upload it. So let's just do gosh, stop it. I hate this software. Logic Pro. Oh, I'm coming, guys. Later. Here we go. So let's put some more in here. So let's drop down and so which ones don't we have? Let's see. Compare. So this is what they got available on Logic Pro. We'd have to look at NEQ, but we're at EQ, NEQ, LES. So let's bring down, let's go in order. So these are considered to be what? Input or output instructions? Yeah. So how many we got? Four or five? That's another thing Logic Pro lets you get by. Did it again. Yeah, I knew that too. Thank you. So the bottom one is actually combined. Okay, so the next one would be compare, not equal to, not less than, greater than. One thing I like about the Siemens PLC is all your commands are in your project window over there. You don't have to go through these. And that's what you do on the Siemens PLC. You click on them, so y'all gonna have to be careful. Watch out for them. Because that's what I'm trying to learn right now. So greater than, less than, or equal to, and then one more. Put it right here. Greater than or equal to. And let's put a coil. Then we'll put a thought I might have put them on the folder on my desktop. These are the programs for the Festo line. We'll look at some of those later on when we get into subroutines. So I just thought I might have put it on there because I know I did it. Just must have did it at home. So which outfit are we not using? Not using any of them right now, are we? I think we might be using one down here. Output 2. So all these other ones we'll use is output 4. That way I want to. Oops. Okay, so we got a counter up here, so we'll use the same source. We got it counting to 50. So how would I address the counter? C5 colon dot ACC, right?
Everything. Address.
Yeah. If he lets us do a cut, let me see if he lets us. Drag it. Didn't know you could do that. Thank you. Learn something new. Oops. Okay, so what are we going to compare the first one to? So it's equal to. Well, all of them's going to be a number. So
Equal to 5.
okay, 5.
10.
We can use the same thing here since it's 5. So. We can use the same thing here too. We can use the same thing here too, right? Less than or equal to. Now let's do something different here. Let's do 10. We can go all. I think we got the counter can go to 50 before it resets. Okay, we're watching our outputs over here. They're right down the line. So we'll start our. No. This is operating off the S4, so I'm not going to hit switches. We'll see how it works. I might change it to a push button, but we'll see. So this should, don't like that, does it? Huh? Let's change this to a push button. Okay, so right now we got what in our counter?
0. So is it equal to 5?
No.
Is it not equal to 5?
Yes.
Okay. Is it less than 5?
Yes.
0. Is it greater than 5? Is it less than or equal to
Yes.
10? Is it greater than 12? Okay. Is it greater than or greater than 10 and less than 30? Less than 30.
Not
It's not greater than 10, right?
Yeah.
So we've got these hooked in an and, so that means both of these have to be true. So which switch am I using? This guy. Okay. Yeah, so saw it switch over here. Is it equal to 5? Yes. Is it not equal to 5? No. Is it less than 5? No. Is it greater than 5? No. Is it less than or equal to 5? Yes. Is it greater than or equal to 5? No. Is it greater than 10 and less than 30?
Oh, it's false.
Yeah.
Go back down.
What's that?
Go back down.
Both of them have to be true.
On that, right there, that greater than or equal.
Yeah.
Oh, that's 12.
Yeah. Is it greater than 10? I probably did. Is it greater than 10 or greater than or equal to 10 or less than or equal to 30? So this is going to be true between the range of 10 and 30. If you use a less than and greater than, it's going to be between them, right? If you use the greater than or equal to and less than equal to, it's going to include the outside. So here's 6, right? Of course, now it's swapped around. Is it equal to 5? No. Is it not equal to 5? Yes. Is it less than 5? No. Is it greater than 5? Of course, these are going to be true the rest of the time. Is it less than or equal to 10? Okay. Is it greater than 12? Okay. So when would our next change are going to be? So this guy here is going to, right? As soon as we get up to 10. Okay, so here we go. Nothing changed, nothing changed, nothing changed, nothing changed. Or did it?
10 now.
Yeah. So we want to go through them. Let's look at the range. Y'all can see how are y'all okay on these? Does it make sense? Everybody okay? So let's go down here. So now the bottom one's true. Why?
Both of them equal to 10.
Yeah, 10, but it's less than 30. We'll go up and 15, 16. As soon as we get to 30, then the bottom one should become false again, right? And here we go, 30, less than or equal to, and now. So we can combine them. I'll try to think of a situation where we can do it in or. Like this is an and. So to get this guy to make the output of these two, both of these true, then both of them's got to be true. Huh? Yes, equal 31.
Rich.
Yes.
In those blocks, the grid, so you can't, well, that, it just doesn't say accumulate. Well, we know that's what it was. That's what it is.
C5.
No. that's where it's coming from. That's accumulated from.
Yeah, that's what it shows. It shows you directly below it. So
Right.
what these instructions does, it shows you the actual number that's in the register that you specify. So this is source B. Of course, down here it's giving it to me in hexadecimal. So A in hexadecimal is equal to 1E in hexadecimal. Sorry, is equal to 30. So this is the contents. Since this is below that, this is the contents of the accumulator of counter 0. And this is also. That's a good point. But you notice every one of them's doing the same thing. Showing you, well, they're showing you what the value of A is and what the value of B is. Understand? So we got this this example too. This is I'm gonna go from the field here. So this is the one that y'all did, and how many timers did y'all use for your? How many rungs did yours have in it? For your lab you're working on now. How many timers did you use? So this is the same program written using what? One timer. Okay. And then we're using what?
Accumulated.
Accumulated website off the time.
And then so we'll see if it does the same thing. So we're using a retenue timer, one timer, where you could get by with 3. Some of y'all use more than that. The problem you have is down there, we try to make that light ring. I'm using that S4 register that we talked about. That automatically gives you it gives you a count. That's the one I was using, which saved me a couple of runs. But this is this program is 5 rungs. Now, does that save time?
Yeah.
Probably not.
I thought you said it doesn't have to scan as much stuff.
Well, unfortunately, the scan is not the number of rungs. The scan is
The number of stuff.
the number of stuff
Just get it.
in the whole thing. So every one of these things count. And what's nice about the Allen Bradley documents is they show you the time every one of these instructions actually takes. So it's the number of instructions in your program that determines the scan time, not the number of what runs. Yeah, we had one guy in our class last time that tried to figure out how many things he could put on a single rung. Yeah, but on a single rung. So we could literally do this whole thing on a single rung. We could start on rung 0 and just put in parallel off rung 0 all the way down, right? And so we could literally do this on one rung. I mean, you could. The rung would get very long and start doing these arrows all over the place where, if you get past what it can display, it starts jumping into arrows. You'll see those things. So right now, what does this say? Well, we're going we have a master start-stop switch, which we call a start-stop station, and then that enables the whole thing, right? Now, I meant to run this off and give y'all that. Then we have a green push button we're supposed to press. What was WSW? Oh, that's the master switch.
Yeah.
Okay. This comes through the red palette light. That's going to cut everything off when it comes through. And then this is going to come on, turn on motor 1, turn on the green pilot light, and it's going to enable our timer at the same time. This is a retentive timer. And then when's the first light, then the next light's supposed to come on after 50 seconds. The time base, by the way, on Logic Pro, they give you a 0.1 time base. I think if you're, I don't know what they got on the 504s, what's the smallest time base they have, anybody work with that? Yeah, I know the Micrologics only give you a 1. So 1 and so this has a 0.1 multiplier. In fact, on Logic Pro, the only time base you have is 0.1. You can't change that over. So so there's 15 seconds. So when we get up to what? When it's greater than or equal to 50, which would be 5 seconds, that's going to do what?
Trigger that.
Yeah, turn on motor 2 and the white pilot light. I forgot to label that. Then, I think it was what? So many seconds later, 40 seconds later. Okay, so that would be what? 50 plus 9. So if it's greater than or equal to 90, right? You understand that? Then what's going to happen? Yeah, the light's going to ring 3 times. I'm using this S4 register. Okay. And then when it gets done, then it'll come back up here and, it's going to ring the bell 3 times. Of course, I had to count 1 more, right? Because it goes, right? Then while the counter's going, when this comes true, it's going to pause my timer because this was one thing I had to work on and this popped up on me when I went from my computer at home, which is running a quad core processor. It's a screen. And it would, when I got on my laptop, I thought it was wrong because it was blinking blood. So slow, yeah. So this is going to pause my timer up there while the bell rings. Why do I want to do that? Because you're supposed to reset it 6 seconds after the last light, after the last ring, right? You understand? So this is going to pause that until my timer gets through. So that's why I decided to use a retentive timer. So while my bell's ringing, the timer's paused. Then after the bell rings the 3rd time, we're going to do what?
Shut all outputs. Turn around.
Yeah, but how we do that? Well, what we do is we got, okay, if it's greater than or equal to 150, I could have used equal to, by the way, here. Then it's going to come in, turn on my red light, it's going to reset my counter, reset my timer, and it's going to set. Because the red light's supposed to stay on. Until I hit my master switch, I stop that, and it's going to reset the whole thing. So 5 lines, but is it going to be shorter than yours? Probably, because I've only used one timer. So y'all all had to use, so this one would probably scan faster because I'm only using 1 timer, right? You understand? So every timer takes up what? A certain amount of scan time. Every counter takes up a certain amount of scan time. And of course, these devices right here take up a certain amount of scan time. So here's my master start stop, right? So say this is the problem with Logic Pro. Yeah, but why? So what you gotta do on Logic Pro, if you gotta normally close contact, you're gonna have to cycle it for Logic Pro to pick it up. See, so it says this contact right here is not true. But say now I cycle it, it's okay. So we sealed in. Now what's it waiting on? Yeah, it's waiting on the green push button. So this is replacing the master switch up at the top that the lab calls for. And okay, so the motor comes on, green light comes on. We don't have a white light, by the way, so I can 5 seconds later, then the bell should come on and ring 3 times. I loaded the program. This is the one that's on my computer. That home one more rating. I didn't save it all yet. Then what's going to happen after the 3rd rating? Well, 6 seconds after the last ring. Red light should come on and kill everybody.
How did you do that with the color of the lights?
Right click,
and Larry figured that out.
right click.
Yeah, just right click on it, and then you get,
Little
look.
circle beside the number right
Yeah, y'all know how to change the switches over, right?
How do you do that?
Yeah, okay, well, you do the same thing, over on the lights, just right click, and these are these are the colors. So you can make them all red, you can make them all green, but you got red, green, and yellow, unfortunately, you can give us a white.
Are those for tentative, or you have to do that for every program?
You have to do it for every program. Yeah, but, well,
I'm just waiting.
I do have a stupid question.
maybe not.
If, we want to go back and review today's lecture, where do we find that on the
It gets the problem with this is that when I record them, they don't go up. What I have to do is I have to upload them to YouTube, and unfortunately it takes longer to upload them to YouTube because it's got to convert it over to the YouTube account. I upload them to YouTube, and then what I do is I have to import them into Blackboard. So that means I have to leave my laptop plugged in and turned on while it uploads to YouTube. If I turn it off when it's uploading, it starts all over.
Okay, I was just curious over on Blackboard on video.
Yeah, this will be there, and like I said, it takes so long to get it up there. What was nice about Tegrity is it would upload anytime I turn my computer on. It would upload in the background. This guy right here, so what I'll do, I'll try to do it when I get home. I'll try to compile it over and I'll try to upload it. But unfortunately it takes so dang long that, I'm behind on trying to get them up there. I think I got like maybe 4 lectures.
There's none that are up on Blackboard.
They should be in recorded lectures. They're not in.
Not even-
Well, they're up on YouTube. I've uploaded them on YouTube.
You may not have enabled that option on our page. I don't know. I'm sitting here looking at it right now.
Does it say recorded lectures? Okay. And this
I would like to recreate this program.
this guy here is a pain trying to get them into Blackboard. Yeah, no, it's blank. There's nothing there. So I haven't put any lectures in there. And the problem is just, it takes so long to get them in there. No, I have to upload them. So I have to upload them to YouTube. And then it takes longer to upload them to YouTube than the actual lecture because it has to compile it over to the format that YouTube uses. And then when they get up there, I have to go up there to YouTube into my channel. I think that's what they call it. And then I have to get a link from that and then import the links into,
Get on Facebook Live.
huh?
Get on Facebook Live.
I believe if you,
For some reason, that Facebook Live broadcast live and then just go back and do it later.
okay, so let's look at everybody okay on compare? Yes, no? We'll see. That's what Kathy says. I'm looking for my PowerPoint. Okay, guys, let's look at the jump instruction. Yeah, y'all go ahead and take a thing away. Perfect time. I'm still looking for addressing modes. Trying to figure out what. Seems like it was in the.
That was gonna help me. You know, I was lucky. You went all the way up. You got that late.
I can see that.
You got that late. Oh, way to go.
What was that post for?
Oh, I did.
The POS. Oh, I'm back. It was. What post? What's it drop down box?
Here we go. Of course, they don't tell you what indirect federalism is.
Rich, what was that pulse for on the other class?
Pulse.
Pulse.
Only thing I know of pulse is you can look at the pulse coder for
I'm talking about the other class.
I don't know that's what you're talking about. Oh, I don't have a hardware key. We have position, which shows you the position. I don't
It was in a drop down box.
pulse.
Yeah. It was something else.
What we do with jump instructions is we deliberately skip over, we tell our program to skip over runs. The first one they look at is what they refer to as unconditional. But really, there's really, as far as I know, not unless you wanted to permanently, if you wanted to skip over some runs for a while, then you would use unconditional. Unconditional means there's no decision made. So the example they give that they're calling a conditional jump is not, unconditional is not true because, why?
You just pushing the button.
You're pushing a button. So it is
Not
a,
making no decision.
yeah, it is making a decision. It's making a decision if the button is pressed
Right.
or not pressed.
Okay.
So when I look at unconditional jump instructions, I mean, yeah, in my opinion, since I've been programming for years, it means it will always jump. So in robotics, if you want the program to always repeat, then this is what you would use. You'd use a jump instruction.
So what's the difference between this and example of both?
Because I don't know what you want. Go ahead. Maybe I'll just.
Like, you're saying that it's just the jump, examining if it's open or closed?
No, the jump
Jump
is
the
here.
output.
Oh, okay.
That's the output.
So this is the jump instruction right here. So the jump instruction changes the flow of the program, or changes the scan of the program. So we can literally make it jump over run. We can jump forward or we can jump back.
Okay, now for this particular logic here, when it jumped down to label
That's right.
and turned that B3 on what, I know B3 could be anything.
Well, what this is saying is B3 is a bit file, right? Okay. So we gotta generate an output. The problem we have is that the jump instruction is an output, a label instruction on the input. So every input, we gotta have what on the output. So what they're doing is this coil right here does nothing. It's just in there to do what? Just to give us an output. To complete the circuit. Every circuit has a load. Does that make sense?
Every circuit has that.
Every circuit has, every rung has to have that load. So this is the load here. What's the function of it? Well, really nothing. Y'all understand that? It's just in there to give a load. Because the jump is what type of instruction?
Output.
Output. The label is input.
And you have to have both of them.
You have to have both.
A label with
And they gotta have the same address.
Q, jumps are Q.
Yeah, it's Q2s. So jumps are Q2s. That's a fix. So a jump instruction has to use Q2. And then we put a colon and specify a word number. Right? So how many, using RS Logic 500, how many jump instructions could we have? 256. Of zero. So how's this guy right here gonna jump? I'm going to, when is it gonna jump?
It's gonna jump when we push the switch. That's it.
Yeah, when we have switch one closed, it's gonna do what?
Leave out on
It's
one.
gonna come here, jump over rung 2, and go to rung 3. No, it's gonna scan. So it's gonna, PLCs automatically scan. So it goes rung 1, normally it goes rung 1, 2, 3, 4, 1, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2. And it does that as long as you go. Right? But if I press that button, it's gonna go 0, 2, 3, 4, 0, 2, 3, 4, 0, 2, 3, 4, if this button is pressed. Because this tells it to jump over what?
So that would be 1, 3.
Jump over on one, go to on 3.
Right? The jump is in 1, 1.
Okay.
You said 0.
Okay. It's still gonna do 0. It's gonna do 0, 2, 3, 4, 0, 2, 3, 4. Is that what
So is it jumping over the?
Jumping over the jump.
Jumping over.
I'm sorry. It's gonna go, thank you. It's gonna go 0, 1, 3, 4, 0, 1, 3, 4, but we're jumping over this guy right here.
That's what
So
I don't wanna
what's the
get jumped.
scenario where you would need to use this?
Jump to another program.
Yeah, and,
Yeah,
What do you mean?
no, we don't have.
why would we want to jump over that push button?
We do have it then. We have FLC.
Decision. No.
Decision.
Decision making.
Well, that's when we do what we call a conditional.
Turn that red light on.
Huh?
I said, we using this in this situation, I know that showing how it works. But if we didn't wanna press that push button to make that red light come on, we'll switch, jump.
What if we wanted to,
Condition that you can just jump for a certain condition. Like if I'm red, I want you to jump to this part of the program.
well, that's conditional, because this is,
Unconditional.
yeah, unconditional means it would always go. So in my opinion, unconditional would never wouldn't have anything. And that would be a situation where if we want to take out a section of a field program and still want the rest of it to run, then what we could do is just put a jump and just jump over the section that we don't want to do.
Okay, so
But you still gotta have an input, right?
No,
You know?
no.
So
And that would be an unconditional jump. You don't have to have an input on the run. I do that all the time. When I'm doing math instructions and stuff like that, when you grab stuff. So, I'll show y'all, the argument.
So without the jump in there, when it scans, it's gonna scan every line of the run period.
Right.
Put the jump in there too.
No, he said without the jump.
Without the jump. So the jump just allows you to eliminate a certain rung or runs.
Wrong.
Right, run
Oh,
or runs.
okay. Right.
So it's more or less troubleshooting.
No, it's a decision making, where you can skip over a rung
if a certain condition is true.
So could it be like the pause on a percentage?
Could be a pause on a timer, or we jump over the timer. But, we could actually use it on a counter. If I wanted to jump over a counter, right, you understand that? Or if I wanted to do, like I wanted to turn on the blower if a pressure switch got up to a certain level, but I wanna jump over it if it's not at a certain level, right, you understand? So we jump over the fan control the whole fan control program. So I could put all this decision making stuff in there, or I could just jump over it if something wasn't true, right? And then if it was true, I could run that. That makes sense. So what we have the ability to do is we can jump forward, or we can also jump what? Back. So I could repeat a run. Let's say I wanted to repeat a run 10 times. Well, see, I could jump backwards. I could jump backwards. I could have a counter every time it comes through. And after the 10th count, I cut off the jump. Then it goes back to the section stand. So we could do something like that. So when this is true, I run a run 10 times, or I run a section 10 times. Right? You understand? But
My problem is doing motor control, you look at ladder.
this is not motor control.
Oh, I know, that's what I'm saying.
And that's something we can't do, or we can do, but it would take a lot of code or a lot of relay. There's not much we can do, in PLCs except compare. We could even do that, we could figure out that too. But the problem is with exclusive ORs, that's what exclusive ORs and exclusive ORs are, they're comparators. But now we're gonna do a lot of relay logic that I could do with one command in what? On a computer. And that's what a PLC is.
What I was getting at within my mind, I'm battling. If I was looking at this in motor controls, every circuit has to be complete. Whereas this,
Every circuit
the
has.
PLC is going to sit there and just scan for everything to see if it.
But you can jump over rungs and ladder logic too, but we'd have to do it we're not jumping over rungs, we're jumping over outputs. Here we're literally jumping over what? We're jumping over rungs. And anything in that rung becomes not true. So there's very little things that we can do in PLCs that we can't do in motor controls. Motor controls, we've been making decisions in motor controls for years. When I worked at US Steel, number 4 galvanizing line had relay houses. And you'd walk into that and there would be 400 or 500 relays in there running one section of the line. They had 3 sections of the line, and they had a relay house for each section. From what I understand, they came in and replaced 90% of that with one PLC. Because now what they used to do with relay logic, they're doing with what? Computers, because we pick up these high level commands that replaces a ton of logic. It replaces a ton of relays, which are electromechanical devices. Now, the problem with electromechanical devices is electromechanical, which means what? We can break down twice. So we could break down electrical or mechanical. And that's your car. Your car is an electrical mechanical device. So you could go out there and it's got a flat tire. Right? You understand? Well, that would be a mechanic. So that's why we got auto people that fix stuff all the time, because cars break down all the time. So here we're replacing this with what?
So yeah, we can do the same thing, Larry, we can do the same thing with relays. But we can also do it with what?
PLCs allow you to call sub routine.
Yes, we ain't got to. Yeah, I don't know of any programming language that don't allow you to use what we call subroutines.
We'll talk about the big advantage of that, and I'll show y'all some of the programs that was written for the Festo line over there. We have those. And what they do is they have a main loop. And what does that main loop do? Well, yeah, but it calls subroutines. And we'll talk about the big advantage of breaking a big program out.
I think Vincent was talking about one program that how many runs?
That's what I'm doing.
And so whoever wrote that program probably didn't use Subroutine.
But basically, they had it broke down, you know, over there in a section like on the left side of the PLC. And you would go, I guess that would be called a subroutine.
Yeah, we'll look at that. And that's, like,
You could click on-
every programming language I've ever seen, uses what we
you
call
click
Subroutine.
on it, go whatever section you want to, just like that.
So let's run this and see it work. Well, I brought the line up. What's nice is that they gave us every one of these programs in Logic Pro. So, as I find,
I done seen them B numbers get up to 275, 565. Be ready.
oh, yeah. Now, when we say it's limited to this is RS Logic. This is 500, right? This is RS Logic 500. We have other languages down there that we've only got one, I think, 5 PLC down there that programs, and it's probably got a lot more features. So it's not the PLC that limits it, it's the what? It's the software that limits the number of registers that we have available to us and what we can address. Of course, this does pretty good. So here we go. What do we need to do? We got it in program. We'll download it and put it up here. This is one right here. Okay, so it's doing what now? Yeah, it's scanning everything, right? Then we'll come over here and do switch 1, and one of the lights should go out. I think it's, which one skipped as a jump? It's 0. So it's output 2.5 is the one out 2.5. Yeah, so here's the one we're jumping over right here. See that? One has got to be closed. Let's see, which one is the jump? 1.0. So which one are we skipping over?
You got the same address. Yeah.
Yeah, 1. You got it closed.
Yeah, but it's supposed to, it looks like this thing's having a little problem.
Same address.
Yeah, it looks like one of them should be a different address because, well, yes and no. So when I close 1, what should happen?
Two, 5, and 1.
You close 1. Wrong 0 and 2.
Now it's working. It wasn't work a while ago for some reason. See, it's not working now.
Because the jump is that address.
You got to jump it.
Bit 0, yeah.
You got it closed. You got it.
Another jump.
They have the output on that.
Oh, yeah, I'm sorry. Now watch this. So right now, thank you. So right now it's what?
Yeah, but look, y'all watch it. Okay. So what I'm gonna do is, right now, 5 is, 2.5 is off, right? LED off, or the light off. And what I'm gonna do is I'm gonna come over here and I'm gonna turn it on. Okay. All right. Okay. And I'm gonna come over here and do this. Okay. And what's it doing now? Now wait, what's it doing now? So notice one is closed and the light is on. Okay, now what would happen if I skip over from 1 to 3? Well, it's not going to scan that input anymore. It's not going to scan rung 2 anymore. Okay, now watch this. Look at this. It's on. I'm going to come over here and I'm going to turn switch 1 off. Here comes switch 1. I'm going to turn it off. Well, what happened to the light? Well, look.
It jumped around it.
Yeah, this guy, okay. It's so what should it be now?
Off. But
It should be off.
But you jumped around it.
But I'm jumping around it. Right? You understand that? So it's not scanning that input anymore because I told my program to jump around it. Right? You understand that? So let's turn it off.
Well, so it's not doing it, yeah.
Okay, here comes a scan right here. Okay, and this is true, so what are we doing? Okay, we're jumping right here. Well, this says this light is supposed to be off, but yet it's what? It's still on. Why?
Because you jumped out.
Because we jumped over it, right? Okay, so let's take the jump out. So what's the jump? The jump is 0. Okay. All right. Notice it turned off instantly. Okay.
Why is the, what's it called?
B3?
The B3 lit up?
Because it's always true.
It's always true.
Yeah, the label is always true.
The label's always true.
Yeah, it's always true.
Okay.
Right, you understand. So this is lit up. So whatever you put out here is always going to be true. Okay, so now I've got it turned off. I'm going to tell it to jump around it. And I'm going to come over here and I'm going to close input 1. But 5 don't come on. Why? Okay, so here we come right down through here. Is the jump true?
Yeah.
Okay, so it's going to jump over that rung and it's not going to scan that input, right? You understand?
PLC's only scan input.
What? Yeah, they scan inputs and they update outputs depending on the input. So that's what it goes. So it scans the inputs, then it makes a decision on what it needs to do with those inputs, and then it updates that.
So in other words, it jumps the last state. So if the output was on. and
It's going to stay. If you jump over it, it's going to stay on.
It's going to stay on.
No matter what's going on. So if that was a compare instruction and I started jumping over, if it was true before I started jumping, the output's going to be true because I'm not scanning that input.
And with off, with the output off, it scanned, it said, I'm already off, so I'm just going to jump.
Yeah, well, that's what it's doing. It's jumping over that rung. So here, so say, notice the output doesn't turn on. Even though I'm closing this switch, the output doesn't change. Now, if I come over here, as soon as I do this, and I turn off the jump, now as soon as I turn off the jump, or go over, I don't jump anymore, then the output comes true. Now I'm jumping over it, now I can come over here and change this, and notice what the output's doing. It stays in the last state, because we're jumping over that input, right, or that rung. And we could go back just as well as we do what? Forward. So if like I said, if we wanted to repeat the same rung a certain number of times, we can put in a counter. Or repeat it for a certain amount of time. We could do it. But then what can we do?
Then we can come in and start adding, so let's look at figure 1110. So how's 1110 work? So we start off with a counter. And this is going to jump which way? So my first jump instruction is down in, where's my first jump? The first jump is in rung 1. And it's going to jump down to the label Q2 colon 1, which is rung 3. Okay. And then my greater, then we've got, in rung 4. And this is going to go to Q2 colon 2. So both of those are jumping forward.
Okay, great. So you saying you're gonna jump backwards, the L.
The label would be in a lower rung number. So the label would be in a rung number lower than where you're jumping.
That's how
So you can jump forward or you can jump backwards. So it all depends on the position of it. So if I was to move this up to rung 1, then you can jump forward. Backwards. So we can jump forward or we can jump backwards. So we might move that rung up. I don't know what that is. It ain't gonna hurt anything, right? That's what I like about simulations. Simulations, you can't do what? Yeah, I can't tear stuff up, yeah. So we'll download it into the PLC. Oh, by the way, there's another thing I noticed about Logic Pro. If you exit Logic Pro, it don't ask you, do you want to save what you got? So be careful with that. It just comes up and says what? Alright. It says goodbye. So be careful with that on Logic Pro. So normally when you exit something or when you upload a new program, it don't tell you do you want to overwrite the programs in the PLC now. So, which is what RS Logic does. RS Logic, if there's a program up there, it comes up and it pops up and says, you're going to overwrite this program in your PLC. Okay guys, so what is this guy going to do? So we can start our counter. Let's change this to a push button instead of a switch. Okay, right now we got this thing set up to count to 10. If it's equal to 5, we should jump over rung what? 2. Rung 2 is controlled by a switch. It's controlled by the, oops, I need to leave this as a switch. So I need to change this to a push button. So we'll go ahead and close the switch. Oops, switch, Rich. Okay. And the light comes on. All right. And then we come up here and count. Oops. I think I already counted. Where do we reset our counter with? Okay. 2. That one. Okay, so right now we got output 2, 1 is energized, right, which is the green light right now. Okay, 1, 2, 3, 4, 5. Okay, now the jump is true. So I'm going to come up here and try to turn the light off. Am I going to be able to turn it off? No. And why is that?
But you jumped it in a state.
Yeah, which is the green light. Now, don't look at the yellow light. Huh? Yeah, it kind of latched.
You jumped it while it was in
Of course, if I needed a latching relay, we'd use what we call a latching relay. Y'all know what a latching relay is? Yeah, a latching relay has two coils on it. One of them we use to latch it, one of them used to unlatch it. This right here might be latched, by the way, I don't know. Of course, if I don't find it, couldn't find the sequence. We use these things on things that can basically kill people if a relay has problems. Out of US Steel, we use them on crane magnets. So if you lost reset on the crane, if they were radio control cranes, everything would drop out, right? So that if you had a load out there on that magnet, what would it do? It would drop it. So magnets were required to use what we call latch and unlatch relays. So when you energize the magnet, you latch it, and to drop stuff, you literally had to do what? Unlatch it. And the PLC simulates that. So we have two coils that work together, right? They get the same number, and they're called what? Latch and unlatch.
I think they're, latch and unlatch. So these two are used in, so you're not gonna have a latch unless you have a what? Unlatch.
Well, you could have a latch.
Yeah, you could. I mean,
Off
well, then when you turn the on switch back on, it would come up and be, disconnect. So, these guys are mechanically latched. So I don't know what this is. You know, mechanical relays have what we call, PLCs, we call it force. Basically what you're doing is you're stimulating inputs or you're forcing outputs, right? Well, generically we call that force. And some of y'all, I know they do that in intro, right? When you force this contact. By the way,
I don't think that, no, we didn't do it.
yeah, you can.
Cause I did.
Yeah.
I did.
I'll look it up. And, you have to turn it on, by the way. So up here on the top. So right now, force is disabled. You enable force, and you can actually run a PLC program without having a PLC, right? Or without having inputs and outputs hooked up to it. You need to be really careful on that because you can get people killed, you know, if you got something active out there.
about the guy over number 8 blast furnace got cut in two up there. I know y'all have that story, right? That's a true story too.
The way we used to put the forces on, we put the force on like, on the bit, so that the operator still had control by pushing the button. You still have control by pushing the button. You push the button, and it goes to the force.
Yeah, but you gotta be real careful, especially forcing inputs and forcing outputs, because you can get somebody hurt. Kill them. We had, so a relay's got a button that you press to force a relay. I almost screwed up too. It wouldn't have killed anybody, but it would sure tore some stuff up. We were working on the number 4 galvanizing line, and back where they weld the strip together, they had side clamps that would come in and clamp the strip down. And that sucker was running wide open, about 700 feet a minute. I was in there forcing a relay, and the guy says, "Hey, you're doing the side clamps." But luckily they was running thin strip that day, and the side clamp was missing. But if I'd have clamped down on that thing, it would have spit steel all over the place. But the guy that got killed in number 8 blast furnace, the guy pushed in the wrong relay. Yeah, and the bottom door, number 8 blast furnace ran what they call a seal. It was sealed, pressurized. So when the belt came up and dropped it into the hopper, they would close the top door and open the bottom door. And a guy was in there working on one of the doors, and they had it locked out and all this kind of stuff, and had it disconnected, and he wanted to push the cylinder out, and the guy went down there and pushed in the wrong relay and closed the other door. They brought him out of there in 2 pieces. So be careful when you force this. Okay, so what we're doing, so we're on our count. So we're skipping over this rung, right? You'll understand that, yes or no?
Yes.
So
We're on 7.
Okay. So we'll come up here and do this now. Oh, wait a second. I think I took it off run. I know I did. Okay, 7. So that jump is no longer true. The other light is being controlled by input 0, 2. So let's go. So here we go. 6 greater than 7. Okay, so now this jump is true. Now I'm going to come up here and close switch 0, and output 2 doesn't turn on. And why is that? Because we're jumping. So what we're talking about, we call these conditional jumps. So these jumps only occur what? When the condition that it checks for is true. Very, very powerful instruction. And like I said, we could do this with ands and ors and ands and or contacts out here, or we could come in and do it with one instruction like this. I think it's last one. Somebody pushed it. We got that powered up on ratchet. So conditional jumps, are you okay? So a conditional jump would already occur if only the condition that checks for it true. The jump and label is what we call an instruction pair, which means what?
Jump.
We don't have one unless we have the other. We have to assign them the same address, and we got to use the Q2, and then of course, whichever one we assign it. So that's the way we can tell where the label goes to. Let's see if we label. I'm not sure on this one, guys. Let's see. I'm going to go to program, and I'm going to give the jump instruction a label. Yeah, it does that. So this would be really nice. If you give the jump instruction a label, then your law will come in here and give you the label the same what. Okay, give you a label. And this is pretty common in programming languages. I mean, every language that I've ever worked with has the ability to do unconditional and conditional jump. Some languages call it go-to. I don't know what Siemens calls their jump instructions. I'll try to find out. Okay, what's next in this chapter?
Master reset.
The master reset.
Master control reset, maybe? MCR?
Yeah, master control reset. So this is the one we just looked at. The master control reset instruction. This is used to stop operation of control systems during high voltage power outages to control systems. We could also use this as e-stop. But what we can do is literally turn off the outputs of our PLC if something happens.
Turn off the output.
Between the two instructions. This is used as an instruction pair. I'll have to look and see what they call the last one. They call the first one MCR, and then the one we jump over. So you don't have to jump over everything, or I'm sorry, you don't have to take out everything. You can specify a section of your PLC when the master control reset is true. So we use this in conjunction. Let's see what it says. I forgot what it is. Yeah. Oh, we can look at the book, right? I got it right here. Oh, we just used the second MCR coil. So we use two. We have to use these in groups of two. So MCR coil when you start, and MCR when you do what? By the way, MCRs are not supposed to be implemented with a It's not supposed, they're supposed to be implemented, the switches have gotta be contact switches, right? You understand that? They actually gotta be like a push button, like an e-stop or something like that. So they can't be soft, they're not supposed to be, I'm sure.
It says like MCR instruction.
Yeah, switch. So, in their example, they probably got that wrong. What are they using? I'm looking at, I don't have this figure in my lab. Yeah, but what's the problem?
Examine the vote.
Yeah, they're using examiner book. So they messed the books wrong. So they show it's true, but, so what should we have there? I'm looking at figure,
Examine
yeah, I'm looking at figure 11, dash 11. And they're using a normally closed contact for a normally closed switch. Y'all understand what's wrong?
push the button, it won't, it'll somehow keep going.
Yeah, I don't have that diagram. Y'all go ahead and take a break. I'm gonna see what they got in the actual Logic Pro diagrams. Figure 1111. They're using. Oh, I think it's right though. So we want the MCR to be false. So that is right.
That is right. Yeah.
So we want it to be false when the input is closed. We don't want it to be true when the input is closed. Understand? Yes or no?
You don't want it. You want it to fail when you open. You want it to see
We want it to be false
it's
when the
right.
input is closed. Yeah, but I'm not running it. So we want it to be false. This is a perfect example when I would use an examine open. Because we want it to be false when the push button is closed. See, so if I come over and do this, so now it's true, see? No, let's see, something's going on.
They make it sound like this is stop.
Well, they're supposed to be, we use these for e-stops. So we're supposed to turn off.
It's gotta be wide. It's a closed button too, so in the PLC, I think it's gotta be the same way. If that's gonna be a stop button.
Yeah, but it's not actually a stop button. When it's active, it jumps over rungs.
Okay.
So this looks like it's backwards.
The MCR instruction will be energized and be activated, therefore, MCR is supposed to be used to move it to a normal.
Okay. Then that is wrong. So we're using switch 2. So right now,
When the MCR is activated, the instructions between MCR instructions are turned off.
yeah, so the book is wrong. What does it say when the MCR is active? The outputs are turned. Yeah, I know, it does a good job. Instruction is connected to the control box. The MCR instructions you've connected on the close. Okay, so it says when the MCR, this is what I'm looking at right here. This is what I was looking for right here. So when it's de-energized, the contacts are turned off. So that means this is backwards. See what I'm talking about? So they have it as an examine open. But if this is, the MCR is not active, it does not. Turns the output off.
It's active, it's just.
No, read it. I got your book. Therefore, when the MCR coil is de-energized, the rungs between the two MCR instructions are turned off. So this is kind of misleading where they display active. So when it's active, it scans them. When it's not active, they turn off. So it is wrong. So if I'm going to use so here's a normally closed push button right there. See, the outputs turn off. Now let's see what happens with a because I think retentive contacts stay true. So we'll put this on a switch down here. Let's put it on 14. Which Q outputs that we're using? Oh, we'll use 4. Oh, Q. No. Huh? I thought we could use anything for latch relay. Oh, this has got to be a different core.
I thought it would be the same, but the output.
So well, on a latching relay, we have 2 different coils. We have one unlatched and we have one latch coil. We'll see. So I was just going by what a real unlatched relay would do. And it should stay latched, right? So that looks like it might be right on PLC. So it didn't unlatch. So the latch,
That's B3.
well, really it could be anything. We can use a B3. That's a good idea. In fact, they just got to have the same. They just got to have the same number.
Well, yeah. Latch, yeah, you know, latches, B3, and the other latch.
Well, it could be an output. You could generate an output from it, but it's so latch, unlatch. Latch. Looks like the unlatch has priority over the latch too. Okay, so let's latch it because I think retentive contacts are supposed to stay true. So my MCR is this guy right here. Yeah. So retentive stay true, which would make sense. Well, I would hate for my magnet to drop that load if I hit the east side.
Use everything. I want him to use that first machine he got now. Mom, he can use everything.
Okay, everything.
Yeah.
I thought you just take that written shit.
Then what are the notes?
I ain't got no notes.
No.
Oh, yeah, well, we gonna have, we gonna
About the sheet that we use now to deal out with. The sheet that we had to put in box. Can we look at it?
No, tell me that. Well, I'm sorry.
Yeah. I went in there and put in, you know, the read, you gotta read both of them. I needed it. But in the book. and put it in. Yeah, and then say, I have two on the last. Yeah, I need to change that.
I knew about it, I forgot.
Right over guide. Right there.
Y'all really fast, like I was really, all that really was coming in like I was, but then I was the emergency stop, I was normally close. I was normally close to sit there, y'all had to see what you doing. I can't even stop out. He was normally concerned, yeah. Right on.
So the which, and then they turn around and figure 11-11 and use a examine closed, right? They use an examine open. So this is the problem we have with examine open. Is switch 0 is closed, and switch, these are both switch zeros, by the way, and both my loads are off. And I'm using a normally closed contact down here. Okay. So I'm on page 253, and I'm reading the first sentence there.
Using a switch, you got switch up and push
Not for 2, which is the one we're using for our MCR.
Okay.
So what we're doing is here's our first MCR coil, here's our second MCR coil. Okay. And of course, I've got switch 1, 0, so these are on the same switch. So 1, 0 is true, but look, notice they're not even lighting up over here.
Oh, so you add the latch and non-latch?
Yeah, I did that because I want to show y'all,
How it works?
well, the latch and unlatch, how it works, but also what a e-stop button does. Normally we use latch and unlatch relays for very high important things that we don't want to go off when we lose our control system. Y'all understand that? So this is what we was talking about a while ago. I've got, and we, like I said, the only thing that I remember out there that we used latch and relays for was on our magnets, on our electromagnets, on our cranes. Because these guys are radio control cranes, and if they lost what we call their reset, it dropped out all the relays that were controlled by the control system. So the problem is that if we lost your reset or somebody hit the e-stop button, we still don't want the magnet to do what? Drop the load. So we use a latch and relay, but we don't kill that output with an e-stop. Y'all understand that? So everything you can kill with an e-stop. That's what I'm trying to show y'all here, what this would do. So if I didn't have it latched, it's okay, right? You understand? So what I'm going to do is I'm going to come up here. The problem is, when I'm looking at figure 11-11, when I first brought it in, they're using an examine open contact, right? You understand? Yes or no?
Yeah. So right now that means that
That's false.
that's false.
Yeah, MCR is not energized, so it's skipping over everything. But that's not what we want. We need to, so if I come over here and change this over to a normally closed open push button, so here's 2, so I'm going to change this over to a normally open push button. Okay. I didn't. Now it's okay. But the problem is, so MCR is active, so it's scanning over the rumps. Everything's fine. But I had to use a what? I had to use a normally open push button.
Y'all understand that? Huh? OSHA says you can't use a normally open push button for an e-stop. Why? Yeah, if the switch fails, you won't be able to do what? Stop. So that means now, if I close it, so here's my MCR, it's what, it's on 2. Then we're going to skip over. So that latch is still okay. So what do we need to do? This needs to be, y'all need to make this correction in your book because it's wrong. I need to do what? This to be examined closed. Now I can come over here and use a normally closed push button. And now everything is okay. So here's, so this is what we're talking about latch. So I'm gonna come up here. I'm using these guys down here. I'm gonna change these to push buttons, by the way. So here's unlatch. Here's 15. Here's latch. Okay. So let's say I do an MCR right now. Here comes switch 2. Right. What about the latch stays what? Latch, and all the other outputs are what? Gone. Let's turn them on. So here everything's on. I'm gonna hit my master. I'm gonna take out my master. So what stayed on? What went off was non-retentive contacts, right? You understand that? The retentive contacts do what? Okay, they are not disabled. The outputs are not disabled. Oops. So he did, whoever written it, I said he, I guess, who wrote this? Raucus, Max Rabi, R-A-B-I-E, did the same mistake that we try to do for motor control, right? If it says we're using a normally closed contact, then by George, we think we got to use a normally closed symbol. But this is not a PLC, it's what the PLC sees as what's a true and what's a false. So examine closed, the PLC sees a 1 as true, right? And examine off, it sees a 0 as true. And when you look at your input registers, this is where it really comes into play with me. I didn't want to do that. So we go back to our project tree, right? Here we can actually look at the inputs. And it don't look like it's working. Oh, I'm sorry, I'm not at the top. So if the switch is closed, it sees that as a 1. If the switch is open, it sees that as a 0, right? Period. And then what does it determine what's true and what's false? What does the program determine what's true and what's false? So we've got this set up for examine closed. We're getting back a 1, so a 1 is true, right? So those are one of the biggest things that people that use PLCs have a problem with. Going from motor controls to PLC. Is that examine if closed and examine if open. So these are available over here if you wanted to just look at what's going on your inputs, right? If you wanted to look on what's going on in your outputs, here's your timers. So here's, it's got 3 registers. We have 2 16-bit registers, the accumulator and the preset. And then we got another 16-bit register, which they only use 3 bits of the 16-bit register. And we call it DN. What's that bit? TT. Timer, timing, and enable. Now these, Allen Bradley, the enable and the timer timing are the same thing, right?
Yeah, they come on as soon as they energize.
Yeah, but I say some of their timers, I don't know if they're I don't know if their high-speed counter, I think their high-speed counter has an enabled one. I'm not sure.
And PRE and HCC are the only ones you, put a dot in front of.
Yes. Well, the other one you put a slash in front of, because it's a bit, inside a register. And then the preset register is a 16-bit register, and the accumulator register is a 16-bit register, right? And then your counter has two 16-bit registers, preset and accumulator, and then it's got this many bits. It's got one for count up, it's got one for count down, it's got one for done. And then one looks for overflow. What's overflow?
Oh, okay.
Yeah. So if you exceed the range of the signed numbers, which the book doesn't do a good job. This is our control register we'll play along later on with. Here's a floating point. Not bringing it up. Integer register. And I don't know why it don't bring up the floating point. So anybody have any problems with the compare instruction? So on the test coming up Wednesday, the review's up there. I meant for it to be up there. I'm sorry I didn't see your email said, because I sent y'all email saying that we put it up. Yeah, I saw yours too, but not, when did I see it? This morning.
I started saying the Friday night.
If you're set up for that texting application, that would probably be the best way.
I never got the text.
I didn't send it because I didn't get a text from you. Normally I use email when I send it out. Sometimes I use text if it's something that we didn't talk about.
Anything but the text.
Yeah, but for some reason I don't remember it popping up on my phone.
One thing I did want.
Oh yeah, I got that.
One thing I did want to ask you about on our third activity, where we have to do the 10 safety.
PLC.
Yeah, the quiz is not a fair. I got it. I just didn't put it up there. You supposed to do a quiz?
No, it's not a quiz. You want to
Safety.
say
Oh, 10 safety rules?
Yeah, and I've searched, there's no, I mean, unless you're in a manufacturing environment, but for PLC, they say there's really no safety precautions.
Well,
You need to be, before something, you need to be looking out there at what you finna force.
okay, so that would be true for, so any safety rules that you have for motor controls will be exactly the same rules that you have for PLC.
Safety glasses.
Well, maybe not safety glasses, but forcing contacts, being aware of power. If you're by the PLC, you got power. The 1100 PLCs that y'all are using down there, not the 1100, the 1000s, those things run off 115 volts on the outputs. 24 volts input, 115 volts output. 24 volts is not labeled, I mean, but we're talking about, so anything, but we use PLCs to control these guys over here. Okay, you understand that? So the same basic safety rules that you have for what? Motor controls or electrical, right?
Basic electrical safety.
Lockout, tag out, right?
Lockout, tag out, right? Still, yeah.
I was taking from a programming point of view. I'm just going to be sitting in front of the computer program.
Well,
I don't want to break
you do, yeah, but sooner or later you're dealing with a PLC. Hopefully you get out and go out and see what your PLC's running. Jeez.
That's somebody else's job.
The guy at Mercedes does it for his house.
That's somebody else's job. Somebody get hurt.
Yeah, somebody get hurt.
Oh, that happened before. What's called, he was at home and the line stopped. We like, the line stopped. We couldn't find out. Why the line stopped. Because he was at home, playing around and stopped flying.
So what exactly is
Anyway, I just want to be clear.
The reviews on there.
Is it on 7 through 11? Because right here it's talking 5 through 11. And down here it says
Well, just read what it says it's gonna be on the test.
We started.
I think there's gonna be symbols, there's gonna be symbols on there. Basically, the symbols are what we're looking for. Ands, ors, nots, nans, nors. We still need to understand those, right? And then some symbols. The timer symbols, legally, where's the symbols at in this book right here? There's one chapter, they give you a bunch of symbols in.
some of the N or.
You were told 180.
You can give us a sheet like that in the process,
What sheet?
with all the bundles of the, logic. With the Boolean equations and all of them.
That would be swell.
No, but, yeah, and chapter 4 has, electrical symbols. Right?
So 4 through 11.
Just symbols. I mean, symbols are in chapter 4. We're not gonna have any, you're not gonna have any, math. We will get back into math, by the way. When we get into our logic operations, your ands, your ors, your nots, your nans.
Okay, so you said no math. That's chapter 10. It's
I don't-
on here.
What's
Math.
that?
Chapter 10, math instructions.
No, compare instructions are on there too. So what we just got through is gonna be with on there too.
Okay, I see that. That's chapter 11.
And wire contacts, I think the only symbols that we have on there are, we have, logic, the relay logic, which we're still dealing with in PLCs, right? And I think the timers is the only symbol that's actually on the test. And I think there's 150 questions on there, something like that. No. I'm joking.
Yeah.